Recording has started.
Alright, welcome back. So today we are going to take this opportunity to review the materials for the second midterm. So as announced weeks ago, so the second midterm will start from October 29th, that's this Thursday, and we will release the PDF of the exam questions at noon. And then you are supposed to upload your solutions also in PDF by Friday, October 30th, and before the noon. So this is the second midterm, and the materials that will be covered in the second midterm is from this lecture 9 to lecture 14. So this is a tip we uploaded to the exam folder in Canvas as well. So let's go through this tip, how to succeed in Midterm2. Topics, basically the MOSFET IV characteristics, and including the subthreshold current. And then we have the CMOS inverter for a few lectures, including the basic operation principle, the voltage transfer curve, the noise margin, and then how to calculate the delay, and then the energy and power of the CMOS inverter. So here are the abilities you're supposed to have. First, to draw and analyze the band diagram of a MOSFET structure. Typically, we use NMOS as example, along the channel direction, and when the gate voltage increases and when the drain voltage increases. So let me open PowerPoint so I can sketch the band diagram for you. So in the first midterm, we talk about the MOS cap, and we show the band diagram along the gate to the channel direction. But in the second midterm, we focus more on the source to channel direction. So that is this one. So we have this band diagram. If this is the source, this is drain, this is the gate. We are looking at from the source to the drain. And then we have the PN junctions, because the source is type. So this is for NMOS. And then the gate voltage, what the gate voltage does, because you need to apply the gate voltage larger than threshold to turn on the transistor by forming the channel. So the gate voltage is going to push down the band. So the band will be pushed down. So you have more electrons that can move over the barrier. And if you want to have a large current, then you need to push down the drain, which means you need to apply drain voltage. So if the drain voltage is applied, then this band is also pushed down. So then you have this slope in the channel. So let me only draw the EC, the conduction band edge. Then you will have the electrons move over, and then like water, they will fall down this slope, and then collected by the drain. So this is how the transistor work from the band diagram point of view. So then let's go back. So understand this band diagram, how it evolves when you apply the gate voltage and drain voltage. And then the MOSFET operation region. So we have three regions: the cutoff, or you can call it a subthreshold, and then the triode and linear, and then the saturation. So understand the definition of those three regions. For the cutoff, then for the subthreshold, the gate voltage is smaller than threshold voltage. And then this one, the Vg minus Vth, the gate voltage minus the threshold voltage needs to be larger than the drain voltage for the triode and linear. And then saturation is the Vg minus Vt should be smaller than the drain voltage. So understand those conditions for the three regions. And then calculate the drain current based on those triode or the saturation current equation using the square law model. That means the first order model, ignore the channel length modulation. So we will review the equations after we are done with this document. So be able to numerically calculate the drain current based on those equations. Of course, the first important thing is that you need to apply the correct equation. That means you have to determine the operation regime first, and then apply the correct equation, and then plug in the numbers for the final numerical value. And then ability to plot and analyze those two curves, okay, IDVG or IDVD. So this is important. So we have two kinds of IV characteristic. One is the drain current versus the drain voltage. The other one is the drain current versus the gate voltage. So the first one is something like this. If we ignore the channel length modulation, then we'll have this turning point that's between the triode and the saturation. So this is at a given Vg. If you change the Vg, you are going to have different curves here. So for example, if you lower the Vg, then you have a lower curve like this. Then the turning point will also change as well. So this is IDVD, and then IDVG is something like this. So this is a threshold voltage, and then here you have another turning point. I should draw this. This is more like a straight line. So there's a turning point here. This is also the boundary between the saturation here and the triode or the linear region here. So you have seen those two kinds of curves before in your homework and also in the practice exam as we discussed last week. So be able to read those curves and then understand how to determine the threshold voltage from those curves and how to calculate the current. So any questions so far? Alright, then let's move on. So understand the saturation current will not saturate if considering channel length modulation effects. So that is to make the current still go up in the saturation. This is the channel length modulation effect. This happens when you consider the pinch-off point of the channel. So here, this is the channel with the electrons. So if you consider this pinch-off point shifting to the left with a larger drain voltage, then the effective L is going to decrease. Then the current will further increase. So this is a second order effect. And we will specify in the question whether you will need to consider this or not. Alright, and then understand the definition of the I on and I off. So this is on-state current and off-state current of a MOSFET. So the definition here, for the on current, we are looking at the VGS equals to VDS equals to the power supply VDD. And the off current is defined when the VGS is 0, but VDS is VDD. So this is related to the subthreshold current plot we are looking at here. So this is also important. So there's one more IV curve you should be able to analyze. That is the log scale of the drain current versus the VG. So this is the same as this one, but the difference here is this is in the linear scale. In the linear scale, you cannot visualize here because this is very small. And we talk about the transistor is not completely off, even below the threshold due to the leakage. So if you draw this in the log scale, you will have something like this. And this is like your threshold voltage here. The off current is here. This is when the gate voltage equals to 0, but the current here is not 0. It's an exponential small number, but it's not 0. So this is I off, and I on is the maximum current here. If you think about the power supply is VDD. So when the gate voltage is VDD, drain voltage is also VDD. Then this is the maximum current you can get, and here in this maximum current, it will always be the saturation current, because here the gate is VDD, and then drain is VDD, so VG minus VT is smaller than the VD, so this must be the saturation current. So this is the on current, that is the maximum current you can get from this transistor. So then understand those two definitions of the on and off currents. And then in the subthreshold, then we talk about the subthreshold slope. So here this slope is the Sfactor. And we say that this one is larger or equal to 6 millivolts per decade. So what does this mean? It means if you want to reduce the current by 1 decade, you need to reduce the gate voltage by 60 millivolts at least. So here, as you have done in the homework, if you want to have 5 orders of magnitude between this I off current versus this current at the threshold, let's say this is I threshold current. If you want 5 orders of magnitude difference here, then your minimal threshold voltage needs to be larger than 300 millivolts because of the slope here. So this Sfactor can be changed by temperature, for example. If you review the equation later, you will see that the Sfactor is proportional to the temperature. So if you have lower temperature, then this Sfactor will be less. Less means more steep in this subthreshold. All right, any questions? Okay, then number 8, understand the difference between N-type and P-type MOSFET, so NMOS and PMOS. So the differences are in the doping, and also the voltage bias is also opposite, like the higher potential, lower potential, which side is source, which side is a drain, is completely opposite in the NMOS and PMOS. So everything is reversed, like VGS, VDS, the definition, threshold voltage, one is positive, one is negative. But to make it simple to use those equations, the suggestion, as we discussed in the lecture for the PMOS, is that to make the absolute values for all the voltages, then the PMOS is like the NMOS. You can use the IV equations. And number 9, understand the basic operations of the CMOS inverter. So here, the important graph is this VTC curve, voltage transfer curve. And understand the definition of the noise margin and the Vm voltage. So let's draw this VTC. So the VTC curve is the relationship of the input voltage and the output voltage of the inverter. So when the input voltage sweeps from 0 to VDD, then the output voltage will reduce from VDD to ground. And then the noise margin is defined when the slope here becomes -1. So here then this part is the noise margin for the low, and this is the noise margin for the high. And this voltage I think is the VIL, this is the VI high. So this is the VTC curve, and of course here if we draw a straight line, then with 45 degree, then you will reach the Vm middle voltage here. So this is the VTC. And then use a matched condition for the CMOS inverter and draw the VTC under unmatched conditions. So if you have matched condition, then the Vm will be half VDD. So everything is symmetric respect to the this Vm points. So that means the noise margin low, noise margin high will be the same, and the transition, let's say the delay, propagation delay high to low, low to high will be the same. So if it's matched, so then we have the matched condition, like the NMOS and PMOS, the drivability in terms of the strength will be the same. As threshold voltage, NMOS and PMOS should be the same. And then unless for the unmatched condition, so you may be asked to draw the VTC if the condition change, right? So if it's matched like this, then NMOS and PMOS, for example, if the NMOS W increase, then how would the VTC change? So we have the rule, NMOS increase W, that means NMOS strength increase, NMOS stronger. So NMOS is for pull down the output, so it will pull down the output earlier, and then this will shift to the left. And PMOS, if PMOS is stronger, then PMOS is for pull up, then this will be shift to the right. So you can use that guideline to determine the shift of this VTC for the unmatched condition. So any questions here? All right. And then ability to calculate the delay in the CMOS inverter using two methods, average current and RC equivalence. So we talk about two methods to calculate the delay. So the delay, you can have the high to low, low to high, the TPHL, TPLH. And then we will specify which method you need to use in the question. And we just say that NMOS is for pull down and PMOS is for pull up. So that means TPHL, you need to use NMOS parameters, and TPLH, you need to use PMOS parameters. And then to calculate the dynamic energy in one clock cycle. So this is a fixed number. Dynamic energy is the energy that due to the charging and discharging of the load cap. And this is also caused by the short circuit current during the transition. So this dynamic energy is due to the input is switching from 1 to 0 or 0 to 1. But no matter what, the dynamic energy will be CV squared, CVDD squared in 1 clock cycle. And then dynamic power will be this energy multiplied by the clock frequency. And then we need to apply the activity factor. So if we switch every cycle, then it's 100%. But if only 10% of the time the input is switching, then you need to multiply this 10% as the activity factor. And we just said that this dynamic power is due to the charging, discharging, or the short circuit current. And then lastly, understand the static leakage power. So this is when the input stay at 1 or stay at 0. There's no switching. But still, as long as you have the power supply applied, VDD is on, then the CMOS inverter is leaking the power because of the off-state current, I-off, as we discussed in the subthreshold current. So then the I-off multiplied by the VDD will be the leakage power for the inverter. Alright, I think that's all key points we are going to cover in the second meter. Any questions? Okay, all good. Then a few tips. Again, nothing is beyond the lecture materials. So please review the lecture notes and the examples in the lecture, as well as your homework questions. And we have done the practice exam last week, and you can review that and redo the homework and review the lecture examples. So you need a real calculator for the numerical calculations, and this is irrelevant. This is for the classroom settings. But since we are open book and open notes, then you can refer to the equation sheet we provided to the end of the exam papers, and we are going to discuss that in a minute. Again, the true or false question, please pay attention to the grading policy. As we discussed a few times, the penalty is applied if the answer is incorrect. So the best strategy is leaving it blank if you are uncertain about it. Again, to get partial credits, write down the appropriate equations first, and then do the numerical calculation. Do not just write down the numbers, then it's hard to justify your approach. Alright, any questions? Then let's review the equation sheet. So here are the equations for the second meter. And the first one is this square law IV model without the channel length modulation. So here, if we ignore the subthreshold current, then the current is almost zero. But if we indeed need to consider the subthreshold current as specified in the question, then you have to apply the subthreshold current equation, which is this exponential equation, and with the subthreshold current. And then the triode or the linear region, so you have this mu n COX, mu n or mu p depends on NMOS or PMOS. Okay, and then W over L, then the VGS minus VT and VDS, and then minus half VDS squared. So this is for the triode or the linear region. And then the saturation current is mu COX W over L. So here, pay attention to this 2. You have a factor of 2 in the denominator. So here, pay attention to this. And then VGS minus VT squared. So this is without the channel length modulation. But if you want to consider the channel length modulation, then here we need to add 1 plus lambda VDS. This lambda is this coefficient to characterize the channel length modulation effect. We will tell you if you need to use this equation or not, by specify whether you need to consider this or not. But if we don't say anything, then you use this here, the equations in the square law model, the black ones. So any questions? Alright, then the on-state current, I on and I off, we just discussed that, so I won't repeat. So the definition of the on-state and off-state current. And then here, this is the subthreshold slope. So this is defined as actually 1 over the slope in the log scale ID versus VG plot. So this is what we discussed here, this one. So if you want to look at what contributes to the S factor, so actually it's 2.3 M KT over Q. So 2.3 is a conversion from the natural log 10 to natural log E. So the base is different. It's like your log 10 or log E. So if you convert that, then natural log 10 is 2.3. And then the KT over Q is the thermal voltage. And you know this at the room temperature is 26 millivolts. But you see the S is proportional to the temperature. So if temperature is lowered, then this S will be smaller. So the slope will be steeper. And then the M here is the body factor. This M, if you express out, it will be 1 plus CDM over COX. So what is a CDM? CDM is the depletion capacitance of the silicon surface. And then COX is the same COX. This is a gate oxide capacitance. So then if you want to further derive, what matters here is the COX is related to the thickness of the oxide. And then the depletion capacitance, the CDM, is related to the depletion width. WDM is the depletion width in the MOSFET. This is what we discussed in lecture 8. So if you use the ratio here of the capacitance, you can make it the ratio with those distance. So here you have the QX and the WDM. So here the 3 factor here is the dielectric constant ratio, or this relative permittivity ratio, epsilon ratio between the silicon dioxide and the silicon, because the COX is oxide, so the permittivity is 4, and the silicon is for the depletion capacitance. Silicon permittivity is 12, so the ratio is 3 here. So this is how we interpret the S factor. So you see that it depends on the temperature, depends on the ratio between the oxide thickness over the depletion width. So this is the S factor. Any questions? At room temperature, okay, so the KT over Q is 0.026 volt, okay, it's 0.026 volt, that is 26 millivolts. And then the kT over Q is the voltage, so the unit is volts or millivolts. That is correct. kT is energy. If you want to use that, it will be like 26 billion electron volt EV, or this 0.026 milli, not milli, 0.026 electron volts for the kT. So kT over Q is the voltage, kT is the energy, and you know the units for the voltage is volts, unit for the energy is electron volts. This is again at room temperature, so this will change as you change the temperature. Alright, then inverter. And the equations in the inverter, first one is this Vm, middle voltage. So here is the equation for the middle voltage. And we have this square roots ratio, Kp over Kn, and you know the Kp and Kn is defined as mu n or mu p, Cox, W over Ln, or W over Lp. So basically the relative strength of the drivability or conductance of the NMOS and PMOS. And then you can plug in the numbers. But if they're matched, then this will be half VDD. So match condition. Threshold voltage, NMOS and PMOS absolute value should be the same. And then this Kn and Kp should be the same. So it's this mu n Cox W over Ln equals to mu p Cox W over Lp. Because typically in the same technology load, the NMOS, PMOS, the Cox will be the same. And they're going to use a minimal L, minimal channel length. So then the spacing between NMOS and PMOS, like the W, the width, the ratio is just inversely proportional to the mobility NMOS and PMOS. And typically NMOS is faster, so then the PMOS should be wider if you want to make it match. And then the CMOS inverter noise margin, so we have a couple of equations, and this only applies when we consider the ideal square law IV with the matched condition. So the assumptions of those equations here for the noise margin, first is the matched condition, second is we only use the square law IV. So here are those equations. And then delay. The propagation delay is defined when the signal propagates through the inverter. And then you have the rising edge and falling edge, or let's say low to high, high to low transition. So it's an average of those two. And then the minimal clock cycle needs to finish the rising edge and to finish the falling edge. So then it's 2 TP. And then the Fmax, that is the maximum clock frequency, is just 1 over the minimal clock cycle. So it's 1 over 2 TP. So this is for one inverter. But when we have the ring oscillator, we have odd number of the inverter collecting the loop. Then the oscillation frequency is 1 over 2 N TP. 1 over 2 N TP. And this N is the number of inverters in the loop. This N needs to be an odd number, like 3, 5, 7. So to calculate the TPHL or TPLH, the first method is the average current method. So it's C, that is the capacitance node, times the VDD, divided by 2IAV. This is average current. And the average current is the average current between the initial currents, it's typically like a saturation current, And then the final current typically is a triode current when the drain voltage is half VDD. So you can get the TPHL this way, and similarly TPLH if you use the PMOS parameters. If we just use a simple RC equivalence, then the TPHL and TPLH will be 0.69 RNC and RPC. So Rn and Rp are the equivalent resistance if we approximate the transistor as a resistor. And then the CMOS inverter gate sizing. So here we are talking about the inverter driving a capacitor load. So if you think about the inverter is driving the external capacitance. So here, if we increase the size of the inverter by S factor, that means S times your W, then the intrinsic delay, this part will not change, because here the capacitance will be increased. Because the capacitance, you need to consider the intrinsic capacitance. So that intrinsic capacitance coming from the gate capacitance and the overlap capacitance of the first inverter. So those capacitance will be proportional to the W. If you increase the W by S, then those capacitance will increase by S. At the same time, the resistance of the inverter here, those equivalent resistance for the transistor will be reduced by S. So the RC, R decrease, C increase. So here the internal intrinsic delay, this part, no change. But the extrinsic cap, this part will be reduced by the factor of S, because the resistance of those transistors reduced by S. So overall, the delay will be reduced if you increase the size of the inverter. Will I go through the practice problem today? No. So we have done that last Thursday. And if you miss that, then you can watch the video. How do we find the equivalent resistance? So this will be given if we ask you to use this method. So we are going to show the equivalent resistance to you. So this has to be approximated. So there's no simple way to calculate that. So this will be given. It's an approximation. And then CMOS inverter, okay, the energy and power. First, the active, dynamic, or switching energy and power. So as we discussed, the energy in 1 clock cycle is C VDD square. And then the dynamic power is alpha C VDD square times F. Alpha is the switching activity, and F is the clock frequency. And for the static and leakage power, so it's simple, it's just VDD times I off. I think that's all for the equations. So, any questions? Can you explain the relationship between the C intrinsic and C extrinsic one more time? Yes. So here in the configuration like this, so the capacitance for this node actually includes the capacitance from the intrinsic capacitance, because here in the first inverter. Actually, we have many capacitance here. For example, so here we are looking at the capacitance that attach to this node. This is a drain for the NMOS, and also is a drain for the PMOS. So if you recall the transistor structure, so then we are looking at this drain, and this what capacitance attached to this drain point. So we have the drain to body capacitance CdV, and then we have the CGD, that is overlap capacitance here. I should draw it overlap. CGD. So you have a lot of capacitance that attach to this drain node. So those are intrinsic to this transistor structure. But here the point is that those capacitance is proportional to the width W of those transistor. As you increase the W, then those capacitance will increase in proportion to this S factor. So this is intrinsic to this structure. And the extrinsic is from the outside. It can be the next stage of the inverter, or can be the wire capacitance. So those are extrinsic to this node. So basically here, typically we just number it as a CL, for example. We just draw a circuit like this when you do when you use this kind of equation here. We just say this is a node capacitance, okay? But this node capacitance actually can be decomposed into the C intrinsic plus C extrinsic. Right. So this capacitance, part of that is coming from this inverter itself, and part of that is coming from maybe the next stage, or this wire may have the preceded capacitance. So you have two parts to contribute to this CL. Okay. Any other questions? If no, then we can end today earlier, and then you will have to prepare for the second meter, and the format is similar as the first meter, and you have 24 hours to work on that. Once again, so we are going to monitor any forum, so then please obey the academic integrity. So you should finish the exam by yourself. All right, that's it for today. Thank you. Bye-bye.